not only we're going to talk about linear regressions, but we'll also look at some scatter plots, because when you do first learn this, you're doing it by looking at scatter plots. So when you look at these scatter plots right here, each of them have some sort of different pattern or some sort of different trend that you can see in it. And you do this in Algebra 1. Anyone remember what type of word we would use to represent this trend right here? This is a positive, yes, and probably a strong positive, yes. This one's definitely positive. What about the second one? Negative trend, probably a strong negative trend. Okay, and then what about the last one? No correlation, no trend. Those words are kind of synonyms of each other. No trend. So when you first start talking about like comparing data, this is how you're first introduced to it, is just by looking at what the trend is. These first two show a linear trend, meaning like in general the dots are kind of scattered around a straight line. But aside from linear regressions and linear trends, there's other types of regressions that we will be doing this semester. So we'll do U-shaped ones, that would be kind of some sort of parabola or quadratic trend. Exponential ones, we'll have those as well. Today we're focusing just on linear ones though. The words that I'm going to be using today are very AP stats. So if you didn't hear some of these words before, that's okay, because these words are geared towards an AP stats class. First thing, talking about what's called a least squares regression line. That is very AP stats. A least squares regression line is an AP stats way of referring to the linear regression equation. Okay, so this is literally the equation that you're writing. Okay, it's the best fitting line for the data. So what the calculator does for us, and when you get to AP stats, you get to learn how to do this by hand, but we're going to cheat and use a calculator. It's the best fitting line for the data. So basically you have your scatter plot, your calculator works real hard to put some sort of straight line through those points, and then it writes an equation for those points. The equation that it writes is the line that minimizes the sum of the squared errors from the line. So what you're seeing here, what the calculator is doing behind the scenes that we're not having to even think about, is it's taking all of these little errors, which are the distance from the actual points, and trying to make those little errors as small as possible, but still put a nice straight line through them. These little errors in AP stats are what are called the residuals. Residual. A residual is the vertical distance that a point on a scatter plot is from the actual least squares regression line, which is the equation that you wrote. The sum of the residuals is always going to be equal to 0. That's more important for AP stats. But what we will be using a bunch today is this equation right here. To calculate a residual, you're going to be doing y minus, anyone know how we'd read that little y with the hat on it? We read it as y hat. That's literally y hat. That is his official AP stats name. Y hat. And it's the observed minus the predicted number. Observed minus predicted number. Observed means like what you actually observed happening, like some sort of actual thing that you timed or actual data point that you have, minus what the equation is going to be predicting for us. Once we have all of our residuals for our set of data, we're going to be creating what's called a residual plot. A residual plot is just like a little graph we make to determine if the equation that the calculator wrote for us is an appropriate fit for the data. Because a lot of times it'll write an equation, but it's a terrible equation. It still does one, but it's not that good. The residual plot should look like a random scatter of points. Okay, so if you see it just randomly scattered around when we make our residual plot on the back, that's a good thing. You want it to be random. If no pattern exists, the model's an appropriate fit for your data, meaning the equation was a good fit for the points. If you do see some sort of pattern, then it's not an appropriate fit. And usually what the pattern will look like is kind of a U shape. Like if you see a U shape going on, that's not a good fit. That means it wrote an equation, but it's kind of a terrible equation. Okay, first thing we're going to do is just make a regular old scatter plot like you learned how to do in 6th grade. But let's read this word problem first. The Great Plains Railroad is interested in studying how fuel consumption is related to the number of rail cars for its trains on a certain route between Oklahoma City and Omaha. What state is Omaha in? Nebraska, good job. A random sample of 10 trains on this route has yielded the data in the table below. So these are the actual observed pieces of information. We actually monitored these trains and we wrote down those trains in this table. Autofocus, let's go. So we have trains A through J, and we have how many rail cars they had. Do y'all know what the number of rail cars are? What a rail car is? It's like you got the engine and then car. They're like the little boxes. And then how much fuel it actually used. And this fuel consumption is in units per mile. They did not tell us the unit, but maybe it's gallons or something like that. Let's make a scatter plot. All right, let's do it over here. Here's our graph. Number of rail cars is on the x-axis, and the fuel consumption is on the y-axis. I already labeled them with numbers. You're welcome. All right, starting with 20 rail cars, had a fuel consumption of 58, somewhere close to 60. I'm going to check them off as I go just so I don't forget any of them. And then 20 rail cars had 52, so we had another train that also had 20 rail cars, but it only used 52. Check it. 3791. Hmm, 3180. You don't got to look at mine, guys. You can just work your way through the table. 3180. 47,114. 43,98. Way up here. Okay. 39,187. Or excuse me, 39,87. 50,122. A little bit above the 120. 4,100. Ugh, finally a nice point. 29,70. Alright, there they are. Does it look linear? Yeah, it does. Looks like they're generally in a straight line and not some sort of U shape or curve. Okay, the sentence in bold over to the left is a very AP stats way of describing this. And usually for AP stats, what they make you do on the free response questions, they don't give you this already filled in. You have to write this whole sentence just like this. So notice there's 3 blanks. There is a blank, blank, blank relationship between the number of rail cars and the fuel consumption of trains on this route between Oklahoma City and Omaha. So again, when you take AP stats, you have to figure out this whole sentence all by yourself. I want you guys to talk in your table and see if you can figure out 3 words that you could use to describe this scatter plot. 3 words, 3 different words. That's only 2. No, not necessarily. You can have strong quadratic. Alright, what's one word we could use? I heard everybody say it kind of all together. Positive. This is a positive trend. Any more information about positive that we want to add? It is a strong positive because those positives are very closely together. You can have ones that are kind of further spread apart, but I'd say that's probably a strong positive. Strong, positive, and linear, meaning it's more of a straight line than some sort of curve or U shape. Again, when you get to AP Stats, you have to write this whole entire description sentence on your own. Okay, using our calculator now. Use your calculator to write the equation of the fitted regression line, which basically just means the equation. It sounds very technical. And then we'll define any variables that we have in the equation. All right, if you haven't yet, let's clear the memory on the calculator. To do that, you're going to press the blue second button, and then the plus sign, and then 712. Sterling, you clear the memory on your calculator? second plus sign 712. You can literally just type 712. Second plus sign 712. It should say RAM cleared. And that deletes off if there were any old scatter plots. It'll get rid of those. Okay. I'm going to write down the steps to do this on the bottom of my paper in case you look back at it later and you're like, how the heck did we do that again? You're going to start by pressing the button that says Stat. Stat. Okay, it's kind of near the left arrow. And you're going to select option 1, which is to edit your data. Option 1, edit. Okay. You should have an L1 and an L2. Okay. In the L1 column, we're going to put our X values. And in the L2 column, we're going to put our Y values. We just need to decide which of these are our X values. What do y'all think? What are the X values? Number of real cars. So these are going to be our X's, which go in the L1. And then the fuel consumption is going to go in your L2 because that's your Y's. And to move around, like once you type one number, you can just press enter or even arrow down will get you the next one. So I'm going to start and press 20, enter, and just go through and get all those X's in. Make sure you don't miss any of them. I usually do all the X's first and then go back and do all the Y's instead of having to go back and forth, back and forth. Any of this feeling familiar yet?
Yeah.
It should be 10. Let me double check that I got 10. 5, 6, 7, 8, 9, 10. Okay. Once you get your X's, you can arrow to the right and put your Y's in the L2 column. Alright. I got them all. You can put your calculator on the table once you get them all, just so I know who has them done, who doesn't have them done. Once again, if you can put calculator on the table if you have them done, just so I know who we're waiting on. Ali, come on, bro. Tiny fingers, type slow. Same with you, Bert. Then you should have your calculator on the table, Bert. Ay, ay, ay. Excellent. Okay, next step. Okay, after that, we're going to go back to stat again. Press stat again. Okay, that same button. Okay, this time we're going to arrow right to the menu that says calculate. Arrow right to calculate. And that pulls up all the different types of regressions that you can do. You might have seen some of these from Algebra 1. There are two options for linear regression, and it doesn't matter which one you use. They both give you a slope and a y-intercept. Just one does it in one order, and one gives you the slope and y-intercept in the other order. Don't ask me why. I usually just use number 4. Right? Normal linear regression where the slope is first and the y-intercept is second. So then we're going to choose option 4, which is a linreg. Linear regression. You can either type the number 4 or you can arrow down to number 4. I usually just type it. And this is where it's just asking, there's a lot of technical stuff that we will do eventually this year. It says, do you want us to use X's for L1 and Y's for L2? Yep, that's where we type them. One day this year we'll learn how to store the regression equations so we can use it, but we don't need that right now. So we're going to go all the way down and arrow down to calculate and then press enter. You can just press enter a bunch of times till you get there. And it should write you a nice long equation with a slope and a y-intercept. Now, are we going to write down all 10 of those numbers? No. We're going to round it. And AP Stats likes you to round it to 3 decimal places. So we're going to round it to 3 decimal places. All right. Let's do it. So we'll have y equals. My slope rounded to 2 decimal places would be what? What's that going to turn into? Sorry, 3 decimal places. Sorry.
1.5, no, 0.150.
Yeah, it would turn into 0.150 to 3 decimal places. So 2.150 or just 2.15 would be the same mathematically. And then we'll put the x next to that. Okay, and the y-intercept, did y'all get the same y-intercept? Just want to make sure we all got the same thing.
Yeah.
Okay. Oh my god, Alan's going to be so happy. 10 points. to 3 decimal places, that would be 677. 677. I wrote this question a million years ago, so I did not make this for the 6-7 trend. 677. Okay, don't move on. Don't move on yet. Okay, this is technically what's called the y-hat equation. This is not just our y equation. This is our y-hat equation. Okay, these are going to create predicted values for us. Okay, so this is not the ones that we actually observed in the table. This creates predicted. So now that we have this, we're going to just label some variables here. What did x represent? What did y represent? Because they asked us to label our variables. What was x? You can see it on the table or you can see it in your graph. Number of rail cars. And what is going to be our y-hat or y? Fuel consumption. It's just going to be our predicted fuel consumption. We'll use it to make predictions. Fuel consumption. It's weird to use the word consumption for fuel because usually consumption, I think you're eating it, but it could also just mean you're using it. Alright, I'm going to take this equation, I'm going to write it on the back side because we are going to need it for all the stuff on the back. So I'm just going to write it up here on the top right so that we don't have to keep flipping back and forth, back and forth, back and forth. 2.150x plus 10.677. Alright, recopy. Excellent. Okay, next interpret the slope of your fitted regression line in the context of the problem. So this first one's asking about slope. Okay, and then interpret the y-intercept, that would be your 10.677, of the fitted regression line in the context of the problem. And this little sentence stems that you see here are what you'll have to write fully by yourself in AP Stats. I've given you the stems so that you can just fill in the blanks, but this is what they fully expect to see. You have to memorize how to write it. So let's read what it says for them, and then I'll have you talk about it in your tables, what you think should go in those blanks. For each increase of, so this is the slope, the 2.15, for each increase of blank for trains on this route between Oklahoma City and Omaha, the model, which remember is just your equation, the equation predicts an average increase of blank units per mile in fuel consumption. So you'll have to figure out what goes in those blanks. Same thing for the y-intercept. Let's read it and then I'll have you talk about it. The model predicts that a train on this route between Oklahoma City and Omaha with blank rail cars would have an average fuel consumption of blank units per mile. Let's talk. What's going to go in those blanks? Give it a minute or so to talk about.
Are we gonna have to write out the whole thing on the test next week?
Oh, and the test is multiple choice. Yeah, because I have to be able to grade them, and I don't want it to take me 30 years to grade.
Miss Ali? Miss Ali?
Who are we still missing?
Miss Ali? No way. So basically, Miss Ali would call Ali. Miss Ali would call Ali. No, call Ali.
Feel free to write in pencil if you think you're going to get it wrong.
Miss Ali would call Ali. Like call Ali. So I know X on the X.
Alright, I saw some right answers walking around. Y'all figuring it out. Yusuf, for the first one, your group. What y'all put for that first blank here? I looked around, I saw that one was right. One rail car. For an increase of one rail car, not just rail cars, specific has to be one rail car. One rail car. For trains on this route between Oklahoma City and Omaha, the model predicts an average increase of how many units per mile? 2.150, yes. 2.150, because that's what the slope actually means. It kind of is a relationship between y over x, so it means fuel consumption per rail car. So 2.15 gallons per mile per rail car. All right, second one. Who thinks they knew what goes into this blank? 0 rail cars. That's what the y-intercept is. So y-intercept is always when the x value is 0. So if you have 0 rail cars, what would be the average fuel consumption? 10.677. How is that even possible that if you have 0 rail cars that you'll still have some fuel consumption, Reba? The engine! You got the little caboose, or not the caboose, the engine car. That's not even one of the rail cars. Have you ever seen one riding by itself, just like the engine car? It's real wonky looking. You're like, where's the rest of it? Okay, up next. We're going to use our best fit line, aka we're going to use our equation that we just wrote to predict the fuel consumption for a train with 20 rail cars. I'm going to have you guys put this answer on a whiteboard. We have the equation. They said we want to calculate 20 rail cars. Go ahead and calculate it and put final answer on a whiteboard rounded to 3 decimal places. Again, let's round to 3 decimal places.
Just plug in this equation.
How many places are we rounding to? Don't say it out loud. Give us a chance to calculate it ourselves.
Even I got it right. Huh? Hey. You guys make fun of me, but on the quiz, who's all this table got it right?
Alright, everybody got an answer? I have to wait till I get my answer too. And boards up, boards up. Let's see those answers. Nice. 53.677. Very good. Again, all we had to do on that one, since rail cars was x, we just plugged that in for x. Okay. Now, let's go back and look at our table. How many rail cars did we just calculate it for? 20. Let's go back and look at our table. Did we have one in our table that had 20 rail cars? Yeah, we actually had 2 of them. Train A and B both had 20 rail cars. And did they have 53.677 fuel consumption? No, one of them was a little higher than that, and one of them was a little lower than that. Okay? I know, that's why it's a prediction, yes. Train A had 20 rail cars. Okay? Train B also had 20 rail cars. Okay? How did the fuel consumption for actual train A compare to what our equation predicted? And then how did the fuel consumption for train B compare to what the equation predicted? So I want you to talk about this in your table. How did it compare? I would like maybe even some exact numbers. Say it was this much higher or this much lower. The equation predicted it this much higher or this much lower. Feel free to flip back to the front and look at what train A actually used and what train B actually used, so that you can determine how much higher and how much lower it is. Let's go, Matthew. Let's take a minute or so to figure out how much higher or lower train A and B were compared to what we predicted using the equation. Talk in your groups if you need to. So maybe just copy the numbers over from the other side and say, okay, actual train A was this, actual train B was this, and it was this much higher, this much lower.
Anyways, yes, I'm gonna do that. What color do you think this is? Can I join? Can I just show up to whatever club I want to and then I sign up? Can I sign up to all of them and then show up to the ones I want to? Hey, well, I know the three I want. Yeah, so how much?
All right. Okay, let's check those answers. What was actual train A? 58. Actual A was 58. And predicted from the equation was 53.677. How much higher was it? 4 point what? 4.323 higher. 4.323 higher. Okay. And then actual B, how much did actual B have? 52? Actual B had 52. The predicted for a train with 20 rail cars again was 53.677. This one was lower. How much lower? 1.677? Lower. Okay. Alright, these little guys that we just found, these are what are called the residuals. This is what is happening here. All these little things like how far away it is from that prediction line. These little guys are residuals. So what we're making next is what's called a residual table of values, and then we'll use that to create a residual plot. Those are our residuals. Notice I have the two that we just did already in our table, but let's read through. The difference between an observed, aka actual, and predicted value is what's called a residual. You just calculated the residual for trains A and B. Fill in the table below to calculate the residual for the rest of the trains. So A and B, you had 20 rail cars. The fuel consumption was 58 and 52 actually, but it was predicted to be 53.677. And so our residual on this one was higher, 4.323. This one I'm writing it as a negative because it was lower, for lower 1.677. So let me do one with these just so you can see what we're doing here. So this fuel consumption here that's filled in all the way across, these are our actual fuel consumptions, actual. Okay. Predicted is this one here. This is what the equation predicts it to be, which is technically your y hat value, and this is your y value. So when we calculate the residual, we're going to be calculating the y minus the y hat. All right, I'll do the first one for you just in case you're lost already. Okay, so on this one right here, are we going to plug in to our equation? Are we plugging in 37 or 91? We're plugging in 37, right? Because this is the x value that we're plugging into the equation. All right, so in my calculator, let's do it. 2.150 times 37 plus 10.677, 90.227. Is that what y'all got? What? I can't see. Yes. 90.227. Okay, and then to do the residual, again, what you're going to do is the y minus the y hat. So for this, it would be literally just top minus bottom. 91 minus 90.227, 0.773. See what we're doing? Okay, and then I'm going to have you finish this table. Okay, finish the predicted fuel consumption using your equations. If you want to do all of the equation ones at first and then do your residuals, or if you want to do one at a time, that's okay too. I'll give you a few minutes to work on that. I know it takes a little while. And then we'll come back together and make a residual plot and then talk about our residual plot. Let's see if we can do this in about 4 minutes. Anyone else have a late bus pass? Late bus pass? Can I have it? So I don't mark it right.
You just swatted.
Make sure you're plugging in the X's, which is the number of rail cars, and not the Y values. Dang, I'm down to the wire. I got a late start. Yes, beat the timer. Alright. Anyone still calculating? Y'all just copying mine instead of actually calculating. Lazy. Lazy. Alright, once you have your residual table, you can create what's called a residual plot. Looking at what a residual plot looks like, it always looks like, I mean, it is technically an X and a Y coordinate plane, but it usually is just a little bit of positives, a little bit of negatives, and then your X value right here. So we're graphing the residuals against the number of rail cars. So what that means is we're going to take the X value, which was number of rail cars, and then plot it with the residual that we found for that X value. For example, if we do the first one, sorry, did I make these in purple? Okay. The first one, train A. How many rail cars did train A have? 20. And what was its residual for the first one? 4.3-ish. So we're going to plot a plot at 20, comma, 4.3-ish. Again, I'm going to check these off as I go just so I don't forget any. The next one also had 20, but what was its residual? Negative 1.6-ish. 1.6-ish. Again, checking them off. So just go ahead and finish plotting those, and then we'll come back together and look at it and compare what we're seeing. Martin, you plotting yours? Done. All right. Y'all ready to describe what we see? No, not ready. Still plotting points. So for the where it says describe the residual plot, this part is kind of just in your own words, not anything AP official yet. Just what do you see? Does it look like they're randomly scattered? Do you see some sort of pattern forming? What do we think? Do we see a pattern or not? Or does it look randomly scattered? Thumbs up if you think you see a pattern. Thumbs down if you think it's randomly scattered around. Do you see some sort of pattern, or is it random? Pattern forming or random? I mean, a pattern forming, or is it random? Yeah, that's random. There's no sort of pattern. It's just like a cloud of points. So I'm going to say for my description, I'm just going to say no pattern exists, or I don't see a pattern, or anything like that. No pattern exists. Was that a good or a bad thing for a residual plot? That was good. Yes, if I remind you on the front, the residual plot should look like a random scatter of points. And if no pattern exists, then the model is an appropriate fit. So I'm going to say that here. No pattern exists. The model is an appropriate fit. And when I say model, it is just a stats word for equation.
Why is it that it has to be random?
Why is it model? I don't know. Oh, why is it that it has to be random? I've looked into that before. It's because if it's not random, then it's basically saying like, hey, you used the wrong type of line. It should be more like this type of line. Like, the model is a good fit. Okay. And then the last question is a very AP stats question. And again, because I'm nice and you're brand new at this, I put a little sentence stem for us where we just have to fill in the blanks. But when this type of question is asked on an AP test, they don't put fill in the blanks. You would have to write this your own self, come up with these ideas yourself. So the last question says, would it be reasonable to use the fitted regression equation, aka the equation that we wrote with our calculator, to predict the fuel consumption for a train on this route if the train had 65 rail cars? Explain. Would it be okay for us to calculate it for 65 rail cars?
Yes.
Yeah, why?
Because there is no pattern.
Because there's no pattern, and we just said our equation is a good fit. So we can use it to do any kind of calculations now. So are we going to say yes or no? Yes. Because there is or isn't a pattern? There is or isn't? Is not. There's not a pattern in the residual plot. because there is not a pattern. The least squares regression line, aka the equation, is a good fit or isn't a good fit? Is a good fit for the data. So it can or cannot be used for predictions. It can be used for predictions, yes. Okay, I'm going to stop.